In this video, we will start with Chapter 5, which is a continuation of linear models and matrix algebra. This video covers Section 5.1, which is on the conditions for non-singularity of a matrix. A matrix A is said to be non-singular if it has an inverse matrix denoted by a to the power -1. To find a solution to a set of linear equations, we must find the inverse of the coefficient matrix. However, we first need to establish the conditions for non-singularity. For this, we need to know what necessary and sufficient conditions are. Necessary conditions states that a statement P will be true only if Q is true. And we denote this by saying statement P and a double arrow towards the right is Q. So P double arrow to the right of Q is a necessary condition stating that P is only true if Q is true. A sufficient condition states that P is true if Q is true, so no only. This is denoted by P with a double arrow towards the left and Q. A necessary and sufficient condition is denoted by P with a double arrow in both directions Q. This states that P is true if and only if Q is true. Some economic examples of necessary conditions. One, the statement P is markets are perfectly competitive, and statement Q is there is perfect information. We know that markets can only be perfectly competitive if and only if there's perfect competition. That means perfect information is a necessary condition for perfectly competitive markets. If we continue with this, statement P is that markets are perfectly competitive, and statement Q says there are no public goods. We know that markets can only be perfectly competitive if there are no public goods. That means it's a necessary condition for perfectly competitive markets. There's an article called Necessary and Sufficient Conditions for the Uniqueness of a Coulomb Equilibrium, published in the Review of Economic Studies in 1987, which I will upload to eCanva. So, what are the conditions for non-singularity of a matrix? First, a matrix must be square. And secondly, we need linear independence by rows or columns. If there is linear independence by rows, there will also be linear independence by columns, and vice versa. How do we find linear independence? It can be tested through the rank of the matrix. And secondly, we establish this through elementary row operations. This is also sometimes now known as Gauss-Jordan or Jordan-Gaussian elimination of rows. Elementary row operations form three parts: interchanging rows with each other, multiplying a row with a scalar k, or thirdly, adding or subtracting multiple rows from another.